Magnetic effects of electric current. We all know that the current carrying conductor produces a magnetic field around it, given by Fleming's right hand thumb rule. The thumb is pointing the direction of the current. The curled finger, obviously the curled finger inward indicates the direction of the magnetic field. So this is something you've already learned in 10th standard, I think, or 9th. You've heard of a scientist called Oersted, O-E-R-S-T-E, Oersted. Okay, we are going to learn in advanced level what is a magnetic. Let's consider a current element here. Current flowing through this wire. We are going to find a magnetic field at any point P, which is dB, due to by dB because it's due to a small current element dL, which is a part of the full length of the wire L. Okay, from here to here, and the position vector is always R. We're trying to find the magnetic field at a point P, which is at a position vector R, from the current element dl. The perpendicular distance between the current element and the point is A. Let theta be the angle between the current element and the direction which you are measuring the magnetic field. Thus, the magnetic field dB at this point is proportional to the I, current flowing through the wire, the dl, the current element, sin theta, the angle, sine of the angle between the current element and the direction which you are measuring the magnetic field, and inversely proportional square of the distance between them. So therefore dB is equal to mu naught by 4 pi, which is the constant I dl sin theta by r square, where mu naught is known as permeability. Permeability in free space, permeability. In electricity lessons it was permittivity. The value of mu naught itself is 4 pi into 10 to the power 7. So when you substitute here, it will be 4 pi into 10 to the power 7, and by 4 pi will get cancelled, so only 10 to the power 7 would remain. Okay. So what will be the unit? Can you imagine this is Tesla magnetic field. This is meter square, the denominator. So Tesla meter square, by mele you have an ampere and a meter. So this and this get cancelled. So mu naught itself is 4 pi into 10 to the power 7 Tesla meter per ampere, and that will be the SI unit of mu naught. So that completes this. And but supposing I want to write this in vector form, dB, they'll ask you in vector form, mu naught by 4 pi I dl sin theta by r square is not a vector, because r is a position vector which is squared. A vector when squared becomes a scalar. So how do I represent it as a vector? Is to multiply and divide by r vector. So therefore this will become dB is equal to mu naught by 4 pi I dl sin theta by r cube into r vector. So the moment you see this, can you notice this? Yeah. Can you see a dl, r vector and a sin theta, which shows it's a cross product basically, because there's sin theta which is dl cross r vector. So ideally you can write this as mu naught by 4 pi I dl cross r by r cube, and that becomes a perfect vector form of writing a magnetic field in a vector form. Okay, so that completes it. So what is the application? This is known as Biot-Savart law. What is this law known as? Biot-Savart law. What does it state? The magnetic field at any point due to a current carrying wire is directly proportional to the current flowing through the wire, the current element dl, the sine of the angle between the current element, the direction which I measure in the magnetic field, and inversely proportional square of the distance between them. Okay, so that completes the definition of Biot-Savart law. What is the application of Biot-Savart law? The first application of Biot-Savart law is something that you have already learnt in electricity lesson, where to find this coil, that there was charge coil, linear charge density. Here it is a current carrying coil. We are trying to find the magnetic field at any point P, which is at a distance of r from the center of the coil, whose radius is A. We are trying to find a magnetic field due to a small current element dl, so it will obviously be dB. So this is the magnetic field dB due to current element dl. It will have two components, one is a horizontal component and a vertical component. Here this is dB cos theta, this is dB sin theta. In electricity we used to put that as dB cos theta, but you know electric field and magnetic field are perpendicular, therefore this is dB sin theta and this is dB cos theta. So supposing you're going to consider an opposite element here, this will again have an electric field in this direction, and so it will have a component dB cos theta here and a dB sin theta here. Therefore the dB cos theta component gets cancelled out because they are opposite direction. Only the dB sin theta remains, and you just have to integrate dB sin theta to get over the entire perimeter 2 pi a of this circular loop in order to find the magnetic field at any point P. So in this you have to take a small subdivision and take a circular coil here and consider the same current element TL, and consider that you are trying to find the magnetic field at some point here, and this is S vector. Okay, and the position rectangle between instead of R vector I've written S vector, that's the only difference. You can even write it as R. In that case, you know, the angle between the R and dl cross R is dl R sin 90. So it's merely dl into R. It's merely dl into R. It's not crossed anymore because sin 90. So therefore I can write the magnetic field in this situation. It will be mu naught by 4 pi into I dl, no sin theta because sin 90 by R square. You may ask me, why have I left the R here? I should be writing R. If I write an R, it will become R cube, so I am leaving it like that. But for differentiating this and the normal R and this special situation that we are learning, I am calling this position vector S vector, so it will be S vector the whole square and dls. So substituting the value of dB in this, you know it's mu naught by 4 pi for dB, I dl by S square, and to sin theta, this is theta, and what is sin theta is opposite by hypotenuse, which is root of R square plus A square. And you know, in this case the position vector will also change, it will also be R square plus A square, so mu naught by 4 pi I dl by root of R square plus A square the whole square, which is R square plus A square into A by R square plus A square the whole square root. So it will be mu naught by 4 pi I A by R square plus A square whole to the power 3 by 2 in integration of dl will give me the magnetic field integrated from 0 to 2 pi A. So mu naught by 4 pi I A by R square plus A square the whole to the power 3 by 2 integration dl is L, upper limit minus lower limit will give me 2 pi A. I know the 2 pi and the 4 pi get cancelled, it will become mu naught by 2 into I A square by R square plus A square the whole to the power 3 by 2. Considering R is equal to 0, which means you are finding the magnetic field B at the center of the coil. Obviously, if R, this distance, R, this is 0, it comes to the center. The magnetic field in the center, R is 0, it will become mu naught by 2 into I A square by A cube, the A and A get cancelled. So mu naught by 2 into I by A is the magnetic field at the center of the circular coil. Very, very important. Mu naught by 2 into I by A. Okay, that is the first application. The second application is to find the magnetic field due to long wire, infinitely long wire. So let's consider point P, which is at a distance of R from a small current element dl, which is a part of a big length of the wire which is L here, the perpendicular distance being A, and you know this is theta, is the angle between the current element, the direction which I am measuring the magnetic field. And can you see this is 90? Let's name this angle as phi, and can you see this right triangle here, which is theta plus phi plus 90 is 180. Therefore theta plus phi is equal to 90, and therefore theta is 90 minus phi. The first observation using the right triangle you are writing. The second observation that you can write using this right triangle is tan phi is equal to opposite by adjacent. So L is equal to A tan phi, but I want dl because I dl sin theta by R square. So dl itself is differentiation of this, which is A into secant square phi d phi. That is the second observation. And the third observation is, you know what is Biot-Savart law, dB is equal to mu naught by 4 pi I dl sin theta by R square. I found what is theta, theta is 90 minus phi. From this I found what is dl, which is this. I want to find what is R square, again from the right triangle, R square is equal to A square plus L square. So R square is equal to A square plus L from the previous statement is A square tan square phi. So R square is equal to A square into 1 plus tan square phi. So R square is equal to A square secant square phi. So I'm substituting all these observations in this Biot-Savart law, mu naught by 4 pi I into instead of dl is A secant square phi d phi, and sin theta will become cos phi because sin theta itself is 90 minus phi by R square is A square secant square phi, secant square phi get cancelled, A and the power get cancelled. So therefore you are left with dB is equal to mu naught by 4 pi into I by A integration of cos phi d phi, and integration of cos phi is sin phi. So dB is equal to mu naught by 4 pi I by A, integration of cos phi is just sin phi. Now imagine this to be an infinitely long wire. Supposing it's an infinitely long wire, okay, so for initially it's not, okay, initially let's consider that you're looking down, so some finite wire, this angle is minus phi 1, and you're standing here and looking up, okay, standing here looking up a finite wire, this is phi 2. So it will be minus phi 1 to phi 2, integrate from minus phi 1 to phi 2. So it will be dB is equal to mu naught by 4 pi I by A into sine of phi 2 minus sine of minus phi 1. We all know sine of minus theta is minus sine theta, so it becomes sine phi 2 plus sine phi 1. dB is equal to mu naught by 4 pi I by A sine of phi 2 plus sine of phi 1, because sine of minus theta is minus sine theta from mathematics. So then consider that this is such an infinitely long wire that if I'm standing here, I'm lifting my head so up to see the top of the wire and the bottom of the wire. This angle that I'm bending my head is 90 and 90, and phi 1 and phi 2 get replaced as 90 and 90. It will become sine 90 plus sine 90. 1 plus 1, which is 2. Therefore dB is equal to mu naught by 4 pi into 2I by A in such a case. So that is for an infinitely long wire. What happens if it's a finite wire and it's a part of a square? Say, imagine the square here. I'm standing here at the center. I'm taking this wire alone on the top. I'm trying to find the magnetic field due to this wire. You know that the way I'm lifting my head to see that this end and this end of the wire will be an isosceles triangle. There will be 45 degree and 45 degree only, because the central angle here is 90. So the same formula, the same formula, instead of sin phi 2 minus plus sin phi 1 will be sin 45 plus sin 45. The whole formula in this case for the blue color wire, the magnetic field will be mu naught by 4 pi into I by A into sin 45 plus sin 45 is 1 by root 2 plus 1 by root 2, which is 2 by root 2. Therefore it will become root 2. Therefore the formula dB is equal to mu naught by 4 pi into root 2 I by A will be the formula for this blue wire. And there will be a current flowing through a wire, and if this is the direction in which the current is flowing, the magnetic field according to right hand screw rule, the curl finger will be pointing outward and B will be outward for that particular wire. Forget about the rest of the coils. So this is just a case study for what happens to this blue wire here. Similarly, let's take an equilateral triangle. Let's consider this wire here, which is again a finite wire, and from here I'm looking at this end of the wire and this end of the wire, making an angle. The central angle will be 160 because 360 by 2. This is 360 divided by 3, I'm sorry, is 120. Therefore, this part of the angle alone is 120. So when you lift your head, it will be 60 degree, and other is 60 degree. So you will substitute as sin 60 plus sin 60 in this. Sin 60 plus sin 60, what is sin 60? Root 3 by 2 plus root 3 by 2, which is 2 root 3 by 2, which is just root 3. Therefore, the formula will be mu naught by 4 pi into root 3 I by E. That will be the magnetic field due to this wire. And if the current is flowing in this direction according to right hand screw rule or right hand thumb rule, you know the curl finger is going to be pointing outward, the B will be outward, and so on. It's just a study for the blue wire, not for the entire triangle I'm seeing, okay? Supposing it's a semi-infinite wire. What is a semi-infinite wire? It's like this, where the magnetic field here I'm trying to find, and I'm standing here, I'm looking at this end of the wire which is infinite. So this angle is being 90, but as here I'm not even lifting my head, so angle is 0. So in the same formula, one of the angle will be sin 90, another angle will be sin 0, sin 0 is 0. So that the formula of dB in that case will be mu naught by 4 pi into I by A, because it is sin 90 plus sin 0, sin 90 is just 1. So for different cases, it's called a semi-infinite wire. For different cases, you will have a different value of magnetic field, and this case study is important for you to be able to do numericals. So that completes the second application of, so if you don't know, see this derivation has not been asked in any exams. See this derivation of magnetic field due to a straight wire carrying current, a straight wire carrying current, or current carrying wire. this derivation is not that important, they never ask, but they ask also the numericals. And to understand all this case study, you should know what is this sin 90 plus sin 90, how did it come, because if you want to find a magnetic field here, you're standing here lifting your head looking at the infinite wire, or it's a finite wire, or it's like this. To understand all that, you should know the derivation, so it's important for you to learn that. Okay, so that completes the two applications of Biot-Savart law. Next comes Ampere's circuital law, which I'll do in the next video.